We're going to take a look at the idea of derivatives with dummy variables. And I'm not sure dummy variables is an official calculus term, so you might not get that if you do a Google search or something like that, but you'll understand what I mean as we go through here. We're going to have a big emphasis on thinking about and understanding what the symbolism means. So let's start with an example that we feel very comfortable with, which is y equals 4x squared plus 7x. Leibniz symbolism, which is pretty nice, would say the derivative of equation y that happens to be using variable x, or the derivative of y with respect to x, and you would just go about your business and do your derivative, but you wouldn't even really give it much thought that this was equation y that happened to be using variable x. Now, if you're comfortable with that, you're probably comfortable with this, but as soon as we switch to w's and a's, people get a little bit hesitant. But this is equation w that happens to be using variable a. So if I do dw dA, I get exactly the same type of answer I get over here. I just have different variables, and it's no big deal. But now we're about to change the game. Take a look at this. This is y equals ax squared plus bx. Now there's letters everywhere. And the request would be for dy dx, the derivative of equation y that happens to be using variable x. That tells me that x is a variable, and that tells me that a and b are not variables. If they're not variables, then they're representing a number, and I have to treat them like a number. Now that's hard on your brain because your brain is used to thinking a letter is a variable. But no, the symbolism here from Leibniz says x is my variable, so a and b must act like a number. So I do my power rule just like normal. Exponent times coefficient, that's how I get the 2a. Lower the exponent by 1, so I could put a 1 there if I felt like it. And here, there's really a 1 there. Exponent times coefficient times x to the 0 power. So the a and the b act just like the numbers 4 and 7 would have up here, but it takes a little bit more brain power for your brain to treat a and b like numbers instead of variables. So that's why I call this dummy variables. A and b are not really variables, they're really numbers. So to continue on with this, I've made up a formula. This is not a real formula, 2 pi r h squared. I'm not sure what that would even be, but that doesn't matter for what we're doing. So I have equation v, and it looks like we have two variables, and we may, but let's look at this very first question. If I were asked for dv dh, that means the derivative of equation v that happens to be using variable h. Okay, that tells me that r is going to be treated like a number. In fact, this entire coefficient, 2 pi r, this is one big number. So this part right here, I can just treat in my brain like it's an 8. So now when I do the dv dh derivative, it's exponent times coefficient. So 2 times 2 pi r is 4 pi r. Take my h and the exponent, lower it by 1. So it just takes a little extra brain power. Now if I'm going to take the same question, but now I'm going to do a dv dr, that's telling me that r is the variable. That means h is a number. Who cares if it's squared? 7 squared means it would be 49. So before I do this derivative, I'm going to do an eyeball adjustment because you're mostly used to a coefficient being in front of a variable. And the way it's written right here, if r is the variable, we have some coefficient or some number, and we have some more number with the variable trapped in between. That's pretty awkward. So I just rearranged the multiplication, and now I have to remember that that really is an exponent of 1, and I'm going to do the dv dr. So that tells me exponent times the whole coefficient, lower the exponent by 1, and anything to the 0 power is 1, so I don't even have to write that. So now I have my dv dr. So you really have to pay attention to the symbolism. What is the symbolism asking you to do? And as soon as you digest what the symbolism is asking you to do, then you can look up into the problem and know what parts to treat like a variable and what parts to treat like a number. Now there's way too many possibilities for me to show you all the different types of examples you could run into. So I'm just going to show you one more here with quotient rule. And your job is to say, okay, if I know my derivative rules and I know what letter is acting like a variable and what letter is acting like a number, I should be able to tackle any one of these no matter how it comes at me. So this is equation A, and right now I don't know which letter I'm going to want to treat like a variable, but when I get this request, dA dW, that tells me I'm going to treat W like a variable, which means V is going to be like a number. So for all intents and purposes, that V is, say, an 8, and this 3V is a 24. I just have to keep my mind thinking like that. So now if I'm going to do this derivative, I'm going to do a low d high minus high d low all over denominator squared. Looks like I have a mistake, and this should be a minus. Whoopsie. All right, so let's see how we got that. When I do the low, I'm just really recopying the low, so that's no big deal. So low d high. When I do the derivative of 3v plus w, if w is a variable, that means v is a number. So this is acting like, say, a 7. The derivative of a 7 is a 0. The derivative of a w, if it's a variable, is 1. That's how I get that nice tidy 1. Minus, this is the high. Now the derivative of the low. Well, if w is the variable, the derivative of 8w is an 8. The derivative of v, which is a number, is a 0. So that whole derivative turns out to be an 8. And then all over denominator squared, we don't care what's a variable. So here we are blending quotient rule with the idea of dummy variables, thinking about the symbolism. This can make your brain overheat, and make sure that you're checking your solutions when you're practicing these types of problems, because you can trick yourself into thinking you're successful, and then it turns out you're not. See you later.